Learn like a pro.
You ever wonder how a scientist can be absolutely sure that a chemical is, well, what it says it is? It's actually a lot like a detective story. Seriously, it's like a forensic investigation, but at the molecular level. They're on the hunt for clues, these little telltale signs that reveal if a substance is pure or if it's hiding something else entirely.
Okay, so let's get into it. Here's our game plan. We're going to start with the fundamental rule of predictability, then we'll set our baseline, see how sneaky impurities can mess with the evidence, look at the cool tools they use for detection, and finally see how it all comes together to triangulate the truth.
First things first, Section 1, Absolute Predictability. See, before we can even begin to spot a fake, we have to understand the #1 rule of this whole investigation. Pure substances are completely, totally, 100% predictable.
So, what are we really talking about when we say pure? It's actually super simple. A pure substance is just made of one thing. That's it. Whether it's a single element, like pure gold, or a single compound, like pure table salt. Just one ingredient in the mix. And because of that simplicity, we get this, our key clue. A pure substance has a sharp fixed melting point and a fixed boiling point. It's not a ballpark figure, it's a hard and fast rule. You can think of it like a unique fingerprint for every single pure substance out there.
All right, on to Section 2. Now, every good detective needs a perfect specimen to compare against, right? A baseline. And in chemistry, our universal standard is something we all know and love. Good old pure water.
And check this out, this shows just how precise those points are. For pure H2O, the melting point is locked in at exactly 0 degrees Celsius, the boiling point locked at 100 degrees Celsius. These aren't just random properties, they're the gold standard, the definitive tests for water's purity.
Okay, now for the juicy part. In Section 3, how impurities interfere. So what happens when a little unwanted guest, an impurity, crashes the party? Well, it immediately starts to sabotage all that perfect, predictable evidence we've been talking about. The very first giveaway is something called melting point depression. Just look at that thermometer on the right. Those pesky impurity particles literally get in the way of the molecules, making it easier for the solid structure to break apart. They drag the melting point down, and, this is also super important, they make it all wobbly, smearing the melting process across a whole range of temperatures instead of one sharp point.
And here's the kicker. It's not random. As this graph shows so clearly, the more contamination you have, the more impurities are floating around, the more dramatic that downward drop becomes. It's a direct clue to just how dirty this sample really is.
Now, for the boiling point, impurities do the exact opposite. Instead of making it easier to change from a liquid to a gas, they actually make it harder. They push the boiling point higher than it's supposed to be. We call that boiling point elevation. And once again, look at that instability. It boils over a messy range, not at one single clean temperature. This diverging scale really paints the whole picture perfectly. You start right there in the middle with pure water and its two perfect, predictable points. But the moment you add impurities, they shatter that predictability. They stretch those sharp points outward into these wide, messy, unpredictable ranges for both melting and boiling. Okay, let's head to Section 4 and see how chemists actually spot these changes. It's time to pop open the investigator's diagnostic toolkit and check out the real forensic tests they use. So, besides just taking temperatures, chemists have another really powerful tool called chromatography. You can think of it like a race. You put your sample on a starting line, and different chemicals, the runners, move at different speeds. A pure substance only has one runner, right? So on the left, you see it leaves just one single spot. But an impure sample, over on the right, reveals all its hidden ingredients as they separate out into multiple spots. There is literally nowhere to hide. And finally, Section 5, triangulating the truth. So we've collected all these different clues, how it melts, how it boils, its signature from the chromatography race. How do we put all of that together to deliver the final verdict? This diagnostic matrix is pretty much the definitive checklist. It's where a chemist compares all the test results side by side against that perfect baseline. Did it melt at exactly 0 degrees, or in a range below that? Did it boil at 100 or in a range above? Did it show one spot on the test or more than one? All the evidence is laid out, plain and simple. So, the bottom line is this: no single test tells the whole story. Just like a detective needs to get evidence from multiple witnesses, a chemist uses triangulation. By cross-referencing the results from the melting point test, the boiling point test, and chromatography, they can nail down a substance's identity and its purity with absolute certainty. And that leaves us with one last thought.
We've seen just how incredibly specific the definition of pure is in a lab. And that makes you think about the world around us, right? From the metal alloys in our phones to the salad dressing in our fridge. If purity is this specific, what hidden mixtures are you using every single day?